Hello. In today's video, we're going to be looking at electron configurations and orbital diagrams. So at the end of this, we should be able to explain how and why the energies for the orbitals of many electron atoms are different from the hydrogen atom, which we've kind of already discussed. We should be able to draw an energy level diagram for our orbitals and populate orbitals and electron configurations using the exclusion principle and Hund's rule along with and we should be able to write the condensed electron configuration for an atom in addition to our regular electron configuration. Okay, so electron configurations are a way of showing our electrons beyond just using our four quantum numbers. So a way of describing the locations of electrons within an atom. With an electron configuration, we show the electrons in their subshells. So it's a list of subshells arranged in order of energy from lowest to highest and gives how many electrons are in a given subshell. Okay, so within our electron configuration, you're going to see the energy level value, 1, 2, 3, 4, so on, and the subshell designation S, P, D, or F. So the shell value, 1, 2, 3, 4, etc., etc., and the subshell designation, S, P, D, F, are given along with the electrons as a superscript value. So for instance, hydrogen, its electron configuration would be 1s1, where that one electron is in a 1s subshell. Our orbital diagrams are just a visual representation of the electron configuration. But with our orbital diagrams, we're putting in actual orbitals. So showing actual orbitals. So it gives a little bit more information. So each orbital is shown as a box. And each electron is shown as an arrow. With our orbital diagrams, we're not only putting things in reference to their energy, but we're also obeying Pauli's exclusion principle and Hund's rule. So for orbital diagrams, Pauli exclusion principle, Hund's rule, and the Aufbau principle are all observed. And we've already gone over Pauli exclusion principle. With Pauli exclusion principle, we can't have two electrons with the same spin. So when we have something like helium, it has a 1s subshell, 1s orbital. So we are going to put our electrons in one spin up, one spin down to satisfy Pauli exclusion principle. But once we get beyond our one electron or two electron species, we need to start to consider what's called the Aufbau principle and Hund's rule. So let's look at both of those things, starting out with Hund's rule. So Hund's rule is going to state that every orbital in a subshell is singly occupied before pairing electrons. This does two things for us. This is going to decrease electron-electron repulsions. Additionally, it's going to maximize the overall spin. If we add electrons in singly first and they're all spin up, we maximize that spin. Next is our Aufbau principle. Our Aufbau principle, we're going to fill electrons in our lowest energy levels first before higher energy levels are filled. So fill electrons within orbital diagrams and electron configurations into lower energy subshells before adding to higher energy subshells. So you'll fill up the bottom ones first, the ones that are lowest in energy before going up in energy. Now, because of energy mixing between our energy levels, this is not always super straightforward. So this right here shows us our arrangement of filling electrons within our different subshells. So if we look, we're going to fill 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5f, and then 6d. So these are the arrangement of the orbitals in terms of their energies. Okay? So let's try this out. Let's give the electron configurations and orbital diagrams of the following: phosphorus and calcium. So phosphorus has a total of 15 electrons. Calcium has 20 electrons. It's always good when you're doing these diagrams to first count how many electrons that you have. And if you look on your periodic table, you can see where the outermost electron is. In the case of phosphorus, if we look on our periodic table, we see that phosphorus is in the N equals 3 level, and it is in a P subshell. So our outermost electron is in 3p. So we're going to stop once we reach 3p. So we'll do 1s, 2s, 2p, 3s, 3p. like so, according to Aufbau principle. And then we're going to add electrons in according to how many electrons can fill in our subshells. So in an S subshell, we only have one orbital, so a maximum of 2 electrons. In a p subshell, we have 3 orbitals, so a maximum of 6 electrons. In a d subshell, we have 5 orbitals, so a maximum of 10 electrons. And in an f subshell, we have 7 orbitals, so we have a maximum of 14 electrons. So you must keep them in mind. So 1s, max of 2, 2s, max of 2, 2p, max of 6, 3s, max of 2. Now we need to use either our periodic table or count and remove how many electrons. We have 15 electrons. We've put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. We have 3 electrons remaining. There we go. But we're done with that one for our electron configuration. Now we can do our orbital diagram. We have 1s, 2s, 2p, 3s, 3p, and our energy is in this direction. We could also do it horizontal, so we can do it vertical or horizontal. Just make sure that you indicate the direction of your energy. And our first orbital has 2 electrons. One will be spin up, spin down. Next is 2 electrons, spin up, spin down. Our next one has 6 electrons. 1, 2, 3, Heim's rule. And then 4, 5, 6. Then 1, 2. And then our last one has 3. 1, 2, 3. We've put them in singly first, maximizing our spin. Next, let's look at calcium. Calcium, look at our periodic table. The outermost electron is in a 4s subshell. We can tell that because it's in the n equals 4 level, and it is in the s block. So it's going to have a 4s electron as its outer electron. So that's where we're going to stop when we're writing our subshell. So 1s, 2s, 2p, 3s, 3p, 4s, and stop. Now, we know our last electron is in 4s, so all the rest of them are going to be filled. We have 2 electrons in 1s, 2 electrons in 2p, 6 electrons in 6 electrons in 2p, 2 electrons in 3s, 6 electrons in 2p, and then when we look, again, we can either subtract or look at our periodic table. We have a total of 18 electrons that are accounted for so far, so we have 2 electrons left to put into our s orbital. Or if we were just to look at our periodic table, we would see that it's the second element in our s subshell, so our s subshell is full. Drawing our diagram, we have 1s, 2s, 2p, 3s, 3p, and 4s. And then we just fill our electrons in. We know all of our other orbitals and subshells are full, including our 4s subshell. So it would look like this. Okay. Now, we have things that are called core electrons and valence electrons, where core electrons and valence electrons are going to be very different in terms of their chemistry. Core electrons are called inner shell electrons. And these are fairly inert. They're not really going to do anything. So they don't react. And they don't participate in bonding. So not doing a lot of anything with that. These are going to be in n values lower than the maximum n value. Generally. And you can usually use your electron configuration to figure out your core electrons. And I'll show you how. Okay. Then we have our valence electrons, or outer shell electrons. And these are the ones that are going to be participating in bonding. They're participating in bonding, they're participating in reactions, so they're doing a lot more. So these are where all the chemistry are at. So for main group elements, so our S block and P block elements, this is going to be the electrons with the greatest N value. However, if we're talking about things with partially filled D or F subshells, then those electrons in the D and F subshells are also considered valence electrons. So for atoms with partially filled D and F subshells, the D or F electrons are also considered valence electrons. Okay. So we can usually see our valence electrons versus our core electrons very well using a condensed electron configuration. This is going to be a shorthand electron configuration. It's also called a noble gas electron configuration or notation because of the use of a noble gas symbol. So it uses the symbol of a noble gas to account for all core electrons. Okay. When we get to our transition metal electron configurations, these are more complicated. And it's because we've started to have an over in our energy levels, switching our energy values for our 4s versus our 3d. So 4s is actually filled before our 3d. So again, it gets very, very complicated. And then of course, 5s is before 4d, 6s is before 5d, so on and so forth. But we still keep in mind our Hund's rule, our Aufbau principle, and all of that. Here are a couple of examples of condensed electron configurations for our transition metals. And as you see, you use your noble gas symbol, and then you put in your valence electrons beyond that. Okay. There are some anomalies in here, but we'll talk about that in just a little bit. Let's also look at lanthanide and actinide electron configurations. So here, we're going down, and we're going to actually have f orbitals in here. So here, there are f orbitals and f subshells. in the electron configurations. Okay. And again, we're going to our 4F, our 3D, and our 6F are all very, very close in energy. So we're going to have a bunch of different mixing within our lanthanide and actinide electron configurations, and these can get incredibly complicated. The only ones that I want you to remember are gadolinium, curium, and then the normal ones. The only ones I want you to remember are gadolinium and curium because they follow a. So fucking tired. I don't want to do this anymore. Oh, that does sound. Almost done. I'm already on 12 of 16. Let's just start this one. Then we have lanthanide and actinide electron configurations, and these are going to be even more interesting. So here we introduce the S subshell. And we're going to have a lot of overlap between the 4F, the 3D, and the 6S subshells. So when you look at the electron configurations here, you're going to see your S, your D, and your F all in there. And they're going to add in some ways that sometimes don't make very much sense, but it's always obeying that Aufbau principle and decreasing those electron repulsions. So trying to get to a lowest energy state, which is why you get some very, very weird things going on where you add in the D electron sometimes, and sometimes you don't. The only ones I want you guys to know are gadolinium and curium. Okay, so we can figure out our electron configurations using our periodic table. I have the periodic table written as it would be written if we were to put the F electron or the F block in the correct place. So we have our S block, our F block, our D block, and our P block. So we can use this in order to figure out our electron configurations. And basically, as we go through, we're going to fill the electrons before. So if we're here, for instance, if we are at that element, we're going to fill electrons in the subshells in the order that they are written until we get all the way here. So we'll have 1s, 2s, 2p, 3s, 2p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5p, and then finally our 6p. So we can add our electrons in this order. This obeys the Aufbau principle. Besides a couple of anomalous electron configurations. So let's use our periodic table in order to figure out our condensed electron configuration. So here it is on our periodic table. If we were to give our full electron configuration Using our periodic table, we see we have 1s, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and then we get to our p block, and we have 1, 2, 3, so 6p3. Here, all of these electrons right here are described by xenon. So these are the same electrons, or the electron configuration of xenon. So we would just write xenon in brackets, and then everything beyond. Okay. Now, as a note, I want to point out our core and our valence electrons. We are dealing with a main group element, so it's very easy. Our valence electrons are our greatest n value. Everything else is going to be a core electron. So in this case, our greatest n value equals 6. So anything that is not in n equals 6 is going to be considered a core electron. So our core electrons are going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 4f14, 5d10. And then our valence are going to be the 6s2 and the 6p3, giving us a total of 5 valence electrons. Okay, let's look at a couple of anomalous electron configurations, so things that don't quite obey the rules. And these they appear to violate the rules we have placed in place for our electron configurations. And the reason these occur is in order to get a half-filled or full-filled state. So irregularities occur to get to a state that is more energetically favorable. So these are going to be half-filled and full-filled states for D block and F block elements. We only see it for our D block and our F block because of how close the S, the D, and the F orbitals are, and because of that, they can do a lot of mixing. So if we can get to a half-filled or a full-filled state, we will promote an electron from an S orbital into a D or F. So to get a half-filled or full-filled D or F subshell, we can remove an electron from the S subshell. So we're going to see this with things like chromium, molybdenum, copper, and silver, where they are not quite at that half-filled or full-filled state, but by promoting one electron into that D shell, we get to that. So for instance, chromium, we would expect AR 4s2 3d4, but that is not correct. Instead, in order to get to that half-filled state, we get AR 4s1 3d5. Okay. Same thing with something like copper. With copper, we are actually going to have AR 4s1 3d10. So promoting one of those electrons to get to that full filled state, which is much more energetically favorable. And then copper only has one valence electron, as all of those D electrons are now core electrons, much more energetically favorable. Okay, the last thing we're going to look at within this unit is electron configuration for ions. And the configurations for ions are going to be based on what type of element we have. Main block elements, these are elements that are going to form ions in order to get to a noble gas electron configuration. So they form ions to get to a noble gas electron configuration. So they either add electrons or remove electrons to get to that octet. So it's pretty easy. We're just going to add or subtract electrons from our electron configuration, and almost always this is going to lead to a noble gas electron configuration. Let's take, for instance, sulfur versus sulfur 2 minus. Sulfur has the electron configuration Ne 3s2 3p4, and then S2 minus is Ne 3s2 3p6. So that same electron configuration as argon. Pretty easy. Same idea, sodium versus sodium plus. Sodium is going to be Ne 3s1, and then sodium plus is just Ne. Or He 2s2 2p6. With our D block elements, we need to take into account if we have a full-filled or half-filled option. So keep in mind getting to half-filled or full-filled states. For your D block and F block elements, it's almost always going to be easiest to write out your electron configuration for the neutral atom first and then remove the electrons from there. It's usually the best way to keep everything straight. Now, when you're removing electrons from your D block elements, you're going to remove electrons from the highest N value first. So this is going to mean those S electrons first. Again, keeping in mind half-filled and full-filled states. With your F block elements, same idea. You're going to remove electrons from the highest N value first, which means first your S electrons, then your D electrons, and lastly your F electrons. So first S electrons, then D electrons, last F electrons. And that is everything for electron configurations and orbital diagrams and the end of this unit. We'll talk to you guys later.